So then I will finish talking about the idea of linearization today, and I'll do an example of it, and we will see how much time we'll do left to do something else. So, so what we found out last time is that in studying all possible equations, or moreover expressions on two variables, we can try to simplify an expression by doing a linearization. So replacing that expression not globally, not everywhere, but at some point. So we fix a point x0, y0, satisfying equation, or in general well, let's say, if you look at equation, take a point and then replace that equation with a linear one. And the replacement happened to be in the form a times x minus x0 plus b times y minus y0 equals 0. And what we found out is that the coefficients a and b should be just derivatives of that function f. So a is the partial derivative of f with respect to x evaluated at that point x0, y0, and b is the partial derivative of f with respect to y evaluated at the same point. So these two are numbers, not functions, after you substitute those values, and therefore it makes the whole equation linear. And so this linear expression replaces f. And what do we expect by replacing f with something like that? It is not f anymore. What's the relation of this to f?
Tangent line at that point.
Geometrically, this is going to be equation of a tangent line to that curve. If this equation thought of geometrically as a curve, then this is going to be equation of a tangent line at that point. What do we expect algebraically? Because at this point we are talking absolutely about algebraic manipulation.
That they're the same. That they're the same quantity.
The same quantity? Do we expect f of x, y to be equal to this? A times x minus x0 plus b times y minus y0. Is that? So are we saying that any function we start with is equal to a linear function?
At a certain point.
At certain point, at the point x0, y0. At certain point, yes. But you know, at certain point, any function is, well, can be equal to any other function. Just add the constant, and you can replace this function with linear with constant function, right? You can say that this function is equal to a constant at that point. So, what's the big deal? At that point, I can say f of x, y equals f of x0, y0, and I have a constant function replacing my complicated function. So what's the benefit of replacing f with a linear as opposed to a constant?
Your coefficients make a vector that you can, use.
Yes, but again, you are heading toward geometric understanding. Algebraically, is there any benefit? What kind of information are we getting about this function by looking at this expression? What kind of information are you getting about the curve by looking at the tangent line? So I give you a point, I give you a line, and I'm saying this is the tangent line to the curve at this point. What do you know about the curve?
You know its behavior at that point.
So I know it passes through that point. Is this the kind of behavior you're talking about? Well, why would I need the whole tangent line? I would say, well, here's the point. The function passes through that point. That's all you need at this point, right? If I tell you that there is a tangent line, am I telling you more about the function? What is it that I'm telling you? The slope at that point. Well, the slope is slope of a line, right? So what's the slope of the curve? So what is it that we are getting about the curve? Other than this point belongs to the curve. Is that a good curve? Why not?
Whether it's positive or negative?
Say it again?
Positive or negative?
Positive or negative what?
You can tell if it, like from the coefficient A and B if it's negative slope, positive slope.
Yes, slope of what? I can see slope of a line, right? And for some reason people are saying that this cannot be the curve. Can it be? My curve that has this tangent line. So you're already able to say that something is not the curve. Can you say something positive?
Well,
that the curve is something?
the tangent line represents velocity, which is speed with respect to time. So it's helping define the future behavior based off of the current line that you're observing. It provides a local piece of a global.
A local piece of a global. So geometrically, what you can only say is that the curve locally looks like this line. Maybe like that. Or maybe like this. All these are possibilities. Maybe like that. Being on one side, on the other side, or crossing. But there is still something. So what is that something? That something is hidden behind these strange words. The curve locally looks like that line. Are we doing mathematics here? Or what? Well, it is a kindergarten. Well, it looks like a bear. And we are all happy. So, is there anything precise we are doing here? Is there any? Well, speaking of numbers, we better do something precise. Because that's what other people expect from engineers, right? Not to tell us that our bridge will look like a bear. What a beautiful bridge. You better stay there, right? And you better do some computations. So what is it numerically that we are gaining about the function by replacing it with that expression?
As you find like points of minimum of the curve.
Well, that is a specific problem that may, well, a solution may use this idea, but But let's stay away from trying to solve specific problems. What kind of information is there?
The x and y variables is a difference. So it's the change in those variables that you're getting in that form.
These two?
Yeah.
Okay. So what about those?
Well, that function at x and y describes the behavior from an original or an origin point to some other point on the curve, and that gives you the slope of your line. So if you choose other points along that curve, then they should follow the same behavior or a similar behavior as you move through the curve.
All right. So now we are shifting the attention to the words like similar behavior. Instead of saying looks like, we are saying similar behavior. What does that mean? So now you're talking about this delta x and delta y. And then this function is replaced by the expression a times delta x plus b times delta y. So what does it mean that behavior of this is similar to behavior of that? Because you know, this can be very complicated. Right? It can be any expression whatsoever. X to the power y to the power x to the power 10 of y. Right? And we can take sine of the whole thing if you want.